Hello students, in this lecture I will be talking about different examples of simple harmonic motion which we have already discussed in lecture 1. So the first example is motion of a body suspended from a spring. So when we take a spring, then there is some spring constant associated with it. When we suspend some body of mass m with it, then because of the weight of this body, the spring get stretched. So let's say in this case, if the mass of the body is m and it exert a force on the spring equal to its mass into gravitational acceleration. So if the length of the spring is L, and after the suspension of the weight on the spring, the length increases by delta L, then there will be a upward force will act on this spring, and that can be given as F is equal to K delta L, where K is force constant. Now in the equilibrium position, when this weight is suspended and a spring is not moving, then in that case these both two forces will be equal, and we can write in this way. Now if we just hold the load to an upper position so that the increased length is now delta L minus x, then in that case the upward force which will be exerted on the body will be F is equal to K delta L minus x, because now the extended length is only delta L minus x. Now the weight of the body will try to pull the spring downwards with a force equal to its weight, and so the resultant force on the body will be like this. And when we will solve, then we will get F is equal to minus kx. So what we see here, that the resultant force on the body is proportional to its displacement of the body from its equilibrium position, which is we have already learned in lecture 1. Now as we already know that the force is equal to mass into acceleration, and we already get this equation, so when we put both equal to each other, then we will get a differential equation which is same as simple harmonic motion equation, and angular frequency will be here. The time period will again be the same as in previous case. Here t is equal to pi by omega, and then putting the value of omega we can get time period. And the solution of this differential equation will be x is equal to x max sine omega t plus phi, where x max is the maximum linear displacement which we can provide, and the phi will be the initial phase. Coming to the another example of simple harmonic motion. So this is simple pendulum. So what is simple pendulum? A simple pendulum consists of heavy particle suspended by a string which is weightless and is flexible and is suspended from a rigid support. Now this is the support S here, and this is the particle which has mass m. This is the string of length L here, and now if we will move this particle with an angle theta, then what will happen? The particle has mass m, so there will be a gravitational force mg to the downwards, and there will be two resultant of this force perpendicular to each other. One is mg cos theta and one is mg sin theta. So mg cos theta will be opposite to the tension T on the string, and this mg sin theta, it will try to oppose the movement of the particle and will try to move it back to its original position. So the force along the string and perpendicular to the string is given here. Now the displacement from the equilibrium position will be L sin theta, where L is the length and theta is the angle of displacement. So this length will be L sin theta. Also, as I discussed, mg sin theta works as restoring force. So it will have a negative sign here, and mg cos theta will be opposite to the tension T, and so it will not affect the motion. Now, in case when theta is very small, it means when theta is less than 15 degree, in that case what happens? The value of theta and sine theta is mostly same when we are talking about the value of theta in radian. So in that case, we can directly put theta in place of sine theta. So L sine theta will become L theta and mg sine theta will become mg theta. So the displacement is equal to L theta. Now if we differentiate it two times with respect to time t, then we will get this, and as we already know that the force is equal to mass into acceleration, where acceleration is d2y by dt square, then we can put this as equal to each other, and then we know that restoring force is minus mg theta, so we will get a differential equation which is similar to the simple harmonic motion equation, and thus this equation will represent the SHM equation for simple pendulum. Again, for time period t is equal to 2 pi by omega, and then is equal to 2 pi under L by g. So the time period for simple pendulum depends on the length of the string and the gravitational acceleration. And the solution of this differential equation can be given as here: theta equal theta max sine omega t plus phi, where theta max is the maximum angular displacement which we have provided, and the phi is the initial phase. Coming to the another pendulum, which is compound pendulum. So the compound pendulum is not like some particle is suspended from a string, but it can be any body which is capable to oscillate freely in a vertical plane when it is suspended at some point. Here it is suspended at point A, and which is called the point of suspension. Now there is center of suspension, which is the point where the axis of the rotation meets the vertical plane through the center of gravity of the pendulum. So there is a body and it is suspended from this point A, and G center of gravity. So what is center of gravity? Center of gravity is the point where the whole mass of the body is appeared to be centered. Now let the distance between this center of suspension A and the center of gravity G is L, and then if we displace this body by an angle theta, then a couple will work on the body, which is given as force into distance, and force here is minus mg sine theta, which we have already discussed in the simple pendulum, and L is the length. So the couple will be minus mgl sine theta. Now this couple is a restoring couple, just like there was a restoring force in the simple pendulum. Now if the moment of inertia of the motion is capital I, and the angular acceleration at this instant is d2 theta by dt square, then from the equation of couple we know c is equal to I d2 theta upon dt square, and we know the value already minus mgl sine theta. So if we solve this, we will get this equation. For the moment of inertia, you can consult in the unit 2 of this paper. Now, if the angular displacement theta is very small, then again we can write sine theta is equal to theta, and then we will get this equation, and then we can write it in this way, which is simple harmonic motion equation. Here, the angular frequency is equal to under root mgl upon capital I, where I is the moment of inertia of the body and L is the distance between center of suspension and center of gravity. Now the time period T will be 2 pi by omega is equal to, of course, 2 pi under root I upon mgl. Now if Ig is the moment of inertia of the body about parallel axis passing through its center of gravity, then from the parallel axis theorem we have I is equal to Ig plus ml square. This theorem you will also learn in the unit 2, and if k is the radius of gyration of the body, then Ig will be equal to mk square. So now if we will put Ig is equal to mk square, then we will have I is equal to mk square plus ml square, and then putting the value of I, we will get the angular frequency omega like this, and the time period like this, and finally it will be here. So if you compare the time period equation with the simple pendulum equation, where the t is equal to 2 pi under root L by G, but here L is replaced by k square by L plus L. So what we can say that here this term is the equivalent length of simple pendulum. So if we take a line on the vertical plane of this length with one as center of suspension passing through the center of gravity, then another end is called center of oscillation. So these are the problems for this lecture which you should try to solve. Here is the solution for the problems which I have given in the lecture 1. So in the first problem, I had asked that try to solve whether these equations are simple harmonic motion or not. So if these are simple harmonic motion equation, then they should satisfy the simple harmonic motion condition. So if we differentiate the equation as here I have done, then you will see that d2x by dt square is equal to minus omega square x. So it means that it satisfies the simple harmonic condition, and thus it is a simple harmonic motion. Similarly, you can solve these three equations. Now for the second one. In the first equation, if we compare it with the simple harmonic motion equation, here it has chosen y, so we can also choose y here in place of x. So y is equal to a sine omega t plus phi. So a is equal to 0.3, omega is equal to 4 pi, and phi is equal to 1.1, which I have written here. A is equal to 0.3 unit. Angular frequency omega is equal to 4 pi radian per second, and initial phase phi is 1.1 radian. Now we have to get frequency. So frequency is equal to f is equal to omega upon 2 pi, which after calculation we will get 20 hertz. And time period is reciprocal of frequency. So 1 upon f is equal to 1 by 20 is equal to 0.05 second. In a similar way, you can solve other two equations. So solve the problems given in this lecture, and then we will talk more in the next lecture.